Greetings, the Astro 30 here yet again with another video for you, and this one we're going to look at the humble and old LM386 amplifier IC. It's actually the LM386N now, and there's three versions of it. They usually have a dash and a number. So the basic parameters of this particular IC is the minimum operating voltage is 4 volt DC. Ignore that, I made a mistake. Maximum voltage for the LM386N-1, probably through to the -3, is 15 volt DC. And for the LM386N-4 is 22 volt DC. However, I wouldn't run these chips close to their maximum because they do get quite hot. And the default gain is internally set to 20. That can be modified by use of a capacitor across these gain pins 1 and 8, which just basically bypasses an internal resistor. Now, looking at it, one would be forgiven for thinking that this is just like a normal op amp or power amplifier IC with a non-inverting and an inverting amplifier input. So you could probably have, like, a negative feedback network going to the negative pin. Well, no. Remember, I just said the default gain is set to 20. There's already a resistor coming from the output back to the inverting input stage transistor network, because the gain is set default to 20 using that resistor. So putting an external negative feedback network here between the inverting input and output may cause unpredictable results. And the biggest problem with this particular IC is it's very easy to get it to oscillate. And I'm going to try and force the IC into oscillation just to show you how easy it is for these things to go into oscillation. It's usually low frequency oscillation like howling, motorboating, stuff like that. Now you can use either of these two inputs and ground the other, so you can have either the input coming into the positive non-inverting input, or you can have the non-inverting input grounded and have the input coming into the inverting input. It doesn't really matter. It will work exactly like an op amp with the predictable results that if you use the inverting input, the output signal will be 180 degrees out of phase with the input signal, just like a normal op amp. Pin 7 here allows us to put a bypass capacitor. Now this comes off of the constant current feed resistor to the input stage. And all this bypass capacitor, and it's usually around about 10 microfarad, all this does is attempts to lower the noise that is present on the input. These ICs are pretty noisy. So putting a bypass capacitor helps to reduce the noise, but not by much. But especially if you're using a 10 microfarad capacitor across these gain pins, because by doing that you end up boosting the gain to 200 just by adding a simple capacitor across these two pins. And then you really do need a bypass capacitor. And the Zobel network is non-negotiable, it needs to be there. The only other problem with boosting the gain to its 200 mark is that this is then really easily prone to going into oscillation, especially when you start overdriving the chip. This is a Class AB amplifier, but it's running on a single supply, and it has a DC blocking capacitor before the speaker. Do not forget to include it. It can be as low as a value of 100 microfarad to a value of 220 microfarad. The data sheet says 250 microfarad, so probably 330, something like that. It doesn't really matter, but the higher the capacitor is, the more bass is going through to this speaker load. Now this particular chip is designed at they say 1 watt, but it's more like a half watt at the end of the day, especially at 12 volts. And they're really designed for driving little speakers like this, or anything up to about 100 millimeter. So that's something to keep in mind, that it doesn't produce a lot of power. However, depending on the size and efficiency of the speaker you use, it can be enough to fill a room with sound. So what purposes could you use this circuit for? Well, if you set the gain to 200 and follow the data sheet, you could actually come directly off of an AM radio detector and amplify an AM radio. It could be the power amplifier of a FM radio. It can be a power amplifier of a stereo cassette deck. You just use 2. Yeah, the applications are really endless. It's wherever you need a small half watt amplifier to drive a speaker. So I'm going to put this on a breadboard now, and we're going to have a look on the oscilloscope of what sort of output powers we can get at different voltages. I'm not going to go 15 volt because I've got the -1 IC. I'm probably going to stay no higher than about 13 volt. 13.8, say it was in a communications radio that was put into a car, for instance. So I'll keep it at 13.8 as the maximum, and we'll see what different power outputs we get into an 8 and 4 ohm load with the different voltage settings here. And I also want to see how low this IC can go before it no longer outputs anything. Okay, so I've got it breadboarded. I've got my Zobel network over here. I've got the output capacitor of 220 microfarads. It's a 63 volt cap, it's the only one I had to hand. And I've got a small 10 microfarad input capacitor, and it's configured in the non-inverting input style. So the capacitor goes into pin 3 and pin 2 is grounded. And I've got an oscilloscope probe measuring what the input voltage is to the amplifier, because there's a pot off screen, a 10 kilo ohm pot, as a volume control, just so I can control where it gets to clipping and back it off, etc., and measure what the actual input sensitivity is at that output and that voltage DC setting. I've also got a dummy load off screen here too, with a second channel of the oscilloscope measuring its output. And currently we're set to 8 ohms. Right, my oscilloscope is turned on, and I'm just going to explain what's what. The yellow trace here is measuring the input, and the blue trace is measuring the output of the LM386 IC into a dummy load. My power supply is already set to 4 volts, the minimum, so I'll just turn him on. Yeah, 4.1, close enough. So looking at the oscilloscope screen, I don't have an input signal going into it yet. We'll ignore the yellow trace, that's just feedback noise from the input pin. But immediately we can see with the output trace, the blue one, it appears to be oscillating. Quite nastily too. So if I was to connect the speaker directly to the output, as we can hear, it's howling. Now remember, I did say that it is pretty easy to get this IC to oscillate, sometimes unintentionally. And there you go, I got it to oscillate. And as we can see, that is pretty nasty. And it's saying it's a frequency of 1.8 kilohertz. However, what was coming out the speaker sounds a lot lower than that, probably about half that, 500. Because it's mainly because of the way that the waveform is. It would sound a lot higher pitched if it was 1.8. Anyhow, so how do we solve that? Is there a problem with the IC? No, there's no problem with the IC. You just have to think about things a little bit more logically. If I put this 100 nanofarad capacitor across the positive supply rail and the negative supply rail, well, look at that. What do you know? The oscillation is gone. Still a bit of noise here coming off the power supply. Why is it so? Well, you got to look at how far the circuit is from the power supply. I'm going through 1 meter leads roughly length, so to it's pretty far from the power supply, so there's going to be a bit of capacitance on this wires here. And most amplifiers, you do need both a high frequency bypass capacitor and a low frequency bypass capacitor, like a bulk filtering capacitor, 100, 220 microfarads, something like that, in order to prevent a circuit that's far from the power supply from oscillating. I can also add in a 470 microfarad 63 volt bulk filtering capacitor and try and get it into the holes. I never liked this breadboard ever since I've bought it, because it's awfully hard to get components in. Right, so I've got the bulk filter capacitor in there. Looking at the oscilloscope screen, we've still got that random noise, but that's mostly noise coming off of the input stage being amplified to the output stage, plus the noise of the oscilloscope probes. But we now no longer have any noise on the output. So again, I'm just going to connect the amplifier to the speaker. I had the leads reversed in the last test. Nothing. No noise. There might be a slight hiss there though. There is, and there's a bit of a slight buzz, which is probably what we're seeing on the oscilloscope screen. So onto the power tests, and I'm going to connect my generator to the pot. I can already see that I'm clipping. It's clipping symmetrically, so that's alright. So if I back that off, I mean I'm using a linear pot, so that makes it more difficult. So there's our input trace or our output trace. According to this, there's 24 volt, roughly millivolt going in, which is producing a 761 millivolt RMS output at 4 volts DC. So what I'm going to do is I'm going to do the test again at various different voltages, write them down, calculate the results, and then show a final diagram or piece of paper showing those different various voltages. I'm not going to film it because it's a long, boring process. So I think I'll go for 4 volt, which we've already done, 5 volt, which is a standard supply, more than 4 volts, so we'll see what the power output is at 4 and 5 volt. Then I will probably do 6 volt, then I'll jump to 9 volt, to 12 volt, and then finally to 13.8. So let me get to doing that. Alright, the power tests have been completed, and that chip was starting to get quite hot. And the results are in, and they're rather interesting. Okay, so here's my little table here. Got the supply volt here of what was going into it, DC. The voltage in RMS coming off of the oscillator or generator. The Vout RMS, power into an 8 ohm load. I didn't actually record the Vout into 4. The power at 8 ohm and power at 4 ohm. Now at 4 volt, their minimum supply, the maximum voltage in, this is the maximum you can put into it before it clips, is 24 millivolts. You get a RMS output of 764 millivolt, which is a power of 72.9 milliwatts into 8 ohms and 93.9 milliwatts into 4. Okay. 5 volt, 29 millivolts, 1.03 volt out RMS. That's a power into 8 of 132.6 milliwatts, or 174.3 milliwatts into 4. 6 volts, input sensitivity is 37 millivolts, RMS voltage is 1.27 volt on the output into 8. That is 201.6 milliwatts into 8 ohms, 255 milliwatts into 4 ohms. So far, these don't look too bad figures. The power into 4 is higher than the power into 8 as expected. Now this is where things start to get a little bit interesting. At 9 volts, the input sensitivity is 60 millivolts. The V out RMS is 2.8 or 2.08 volts into 8. That's 540.8 milliwatts into 8 ohms and 600.6 milliwatts into 4 ohms. And there's a star here because I had to retest it. That's just what that means. We can see for the above figures, the power seem a lot further away from each other, between 8 and 4. But now we get to here, it's getting very close. So at 12 volt, this is where it does get interesting. We've got an 80 millivolt input sensitivity, 2.81 volt output voltage into 8 ohms, 987 milliwatts into 8 ohms, and only 828.1 milliwatts into 4 ohms. So the power is now a lot less. Why? I'll explain that in just a sec. 13.8 volts. We have a 96 millivolt input sensitivity, a massive 3.15 volt output swing RMS, which is 1.24 watts into 8 ohms and only 801 milliwatts into 4. The reason why the powers into 4 are starting to drop off is because A, we're coming to the absolute maximum ratings of the IC, as in voltage supply, and the chip is starting to get hot, so it's starting to become more efficient at those powers. If it was heat sinked, it would probably work a lot more efficiently. Also, above 9 volts into 4 ohms, it starts to clip asymmetrically, so it's not a symmetrical clip. The top starts clipping a lot earlier than the bottom, or the positive starts clipping earlier than the negative. So those are my test results. I did find them interesting, and I am quite impressed with the results at 12 volt. It's almost 1 watt RMS. And I'm not sure what the peak value is. You'd have to reconvert the RMS voltage back or retest it into the half peak voltage and then calculate. But it would be definitely over a watt at 12 volt and close to a watt at 9 volt, probably about 800 millivolt at 9 volt. But there is a significant increase in power between 9 volt and 12 volt. So the sweet spot of this LM386 operating range is between 9 and 12 volt, where you get the most power out of it. Okay, so I'm in a 4 ohm load now and at 9 volts. As we can see, if I amplify that, it's starting to clip at the top, but the bottom seems fine. So it's not actually clipping symmetrically. In fact, it's asymmetric even more when it's driven into distortion, that the negative going side of the cycle is clipping more than the top. So it's definitely an asymmetric clip. I'll bat that off because I don't really want to overheat the chip, because they're $3.25 each from JCar. They're quite expensive for an old IC. So I'll go up to what I'm going to consider the maximum supply you should be giving the LM386 N-1 anyway, which is 12 volts, into 4 ohms. Yeah, it's very definitive. That's why the power start falling off after 9 volts, is because of this asymmetrical clip. And driving it into distortion, it's actually made the top worse and the bottom is still clipping less than the top, and it's a bit of a difference between 9 and 12 volts. So yeah, really, this IC does not like driving a 4 ohm load at those power levels or voltage supply levels. It's fine up until 9 volt, but after that you're not going to get much more out of it than you would into 8. So that's something to keep into mind. And we can also see what it's doing to the input signal. Once it symmetrically clips here, it's making the input signal look very jagged, for want of a better term. It's almost like a shark tooth. Again, that's why we were getting noise when no input signal was connected back into that channel, is because when this IC was oscillating, it's just feeding back into the input circuitry, and that's exactly what it's doing to the waveform, is because of that feedback into the input circuitry, because of the asymmetrical clipping. Back it out of clipping and the waveform looks almost perfect. So we know that this IC obviously has limitations, but it's still impressive for a 40-year-old odd IC that was made by Texas Instruments. I don't know who made it originally, but it's about as old as the LM741. So they're about roughly the same time. And as I said, this has an internal gain set of 20 in the start, and it was designed up from scratch for that purpose, to have a default gain of 20. Because this particular IC was designed to be put into TVs to power audio, sound and radios and stuff. That's why they made it. I almost forgot, whilst concluding this video, to do the minimum voltage test. So I'm going to do that now. The supply is set back at 4 volts. Turn him on. We have an output. I'm not measuring the input anymore. It's not kind of necessary at this point. Back that off a little. I'm going into an 8 ohm load still. So I think we'll go down to 3.5 volts. Thereabouts.
It's starting to flat top, so I need to back off the signal. In fact, I might remove the gain boost that I've got in there. There we go. So yeah, we're still outputting about 500 odd millivolt RMS. So we'll go down to 3 volt. We still have a signal, albeit it's flat topping. Yeah, 350 millivolts output. Okay, it's still amplifying. This supply doesn't go any lower than about 2.6, so that's where I'm going to wind it. Well, in this case 2.8. I can't go any lower on that supply, but it's still operating, even though the data sheet says the minimum requirement is 4. But it will work quite happily on 3 volt, although you're only going to get 350 millivolt out, which into an 8 ohm load is not going to be very powerful. 37.8 milliwatts, but it still amplifies. Alright, so I've reconfigured the circuit as per the data sheet using a 10 microfarad capacitor between pin 1 and 8. Positive of the capacitor goes to pin 1 as per data sheet, and that should give us a gain of 200 now. And there is the 10 microfarad capacitor there, going across pins 8 and 1, so negative going to pin 8, positive going to pin 1. Or you can use a bipolar capacitor, it doesn't really matter. All that's now effectively doing is bypassing the one of the global feedback resistors from the output back to the input stage. Power supply is set to 12 volts, turn him on. 11.9, close enough. Going to that, 300 mA current draw. What is going on there? That should be 0. Okay, something's obviously clearly wrong here. There's no input signal connected. It's clearly oscillating and feeding back into the input. So as I said, it's very easy to get this thing to oscillate. Well, it doesn't like to play nice with a gain of 200 for whatever reason. It was working fine yesterday. Today it's got stage fright and decided to go into hiding. It was oscillating around between 8 and 16 kilohertz, which is quite high pitched. I played around with the filtration here, that made no difference. I disconnected the pot completely from the input and the oscillation was still there, but it wasn't as bad. It dropped from 16 to 8 kilohertz, but yeah, it doesn't like it for whatever reason. So I've now reconfigured it to use a gain of 50 with a series resistor between pin 1 and the electrolytic capacitor, 10 microfarad. As per the data sheet, it's supposed to be a 1.2 K resistor. I've got a 1.3 in there, so it's probably more like a gain of, I don't know, 47. And still at 12 volt power supply, or 11.5 now. There's no oscillation, and we have an output signal. And there's clipping there. So at 12 volt we've got a VRMS in of 35 millivolts for the full 2.65 volt RMS out. I do apologise with the gain of 50 test what the input voltage was. For some reason I'd forgotten to reconnect my input probe, so I don't know how it was measuring anything. Let me just quickly recorrect that test. Alright, so our actual input voltage RMS is 10 millivolts more like, which according to my figures is about right. So yeah, we're close to that, a little less maybe. Still 287 milliwatts. So as to why it started oscillating like that, it's most likely because of its layout. The layout for this particular IC is fairly critical when you're putting it onto a PCB, for instance, because as I've said multiple times through this video, it is very easy to get this IC to go into oscillation. So where to now from here? Well, I guess what I should do is two more things. One is with the current capacitor values here, not too worried about what the gain is, it's irrelevant at this stage, but with a 220 microfarad output capacitor and a 10 microfarad input capacitor, what is our actual frequency response? Right, so currently I've got 1 kilohertz going into it, and roughly the waveform is between the two gradicules on the screen, so it's going to be the same voltage. It's about 1.6 volt RMS out. So I'll just play with the frequency. So at 100 Hertz, we've got a significant drop. So 200 Hertz, the voltage is starting to come back up. 300 Hertz, it's right back where it started. Probably a tenth of a volt less. So okay, that's fine. So we know that around about the 300 mark is where the voltage starts to come back up. So 250, 90, yeah, I'm going to say 300. At 400 Hertz we are bang on the money. So it's going to start rolling off around about 350 Hertz with these current capacitor values. A larger output capacitor probably will give you a little bit more bass. So let me just change the frequency up into the upper kilohertz range. So I want that. Alright, so I'll zero that back out. Okay, so at 2 kilohertz, not much has changed, still 1.59 volt RMS out, 3, 4, 1.55, 5, 1.55, 6, 1.54, it's starting to roll off, 7, 1.54, 8, 1.54, 9, 1.53, so it is starting to roll off. Need another digit. Okay, so at 10 kilohertz we're at 1.53 still, 20 kilohertz 1.53. So 22, 23, 24, 26, it's still actually staying relatively around the 1.54, 1.53 mark. So it's up to 34 kilohertz now and it's not rolling off. Even at 67 kilohertz it's still not rolling off. That's quite an amazing frequency response, although the waveform is starting to look a bit silly. The actual voltage has actually increased to 1.66 now, and we're at, like, you know, 111 kilohertz. So the frequency range is definitely going to be good for 300 hertz to 22 kilohertz without the frequency rolling off so much. So yeah, that's the frequency response to that is pretty good. Alright, next test I'm going to do is a current test, like how much current is this thing drawing between nothing, idle, and, well, full power output at a 12 volt supply. So the meter is connected backwards for all intents and purposes. I've got the leads around the wrong way. We're seeing a current draw at idle with no input signal of 6.25 milliamps. So its idle current is around 6 mA. So I'll wind this up until we get to clipping. Clipping's there, back it off. About 143 milliamp current draw at full power at 12 volts. So on a 9 volt battery, for instance, even though this is 12 volts, that is quite a significant draw. It's around about probably the 120 milliamp mark at full power, so it is going to drain the battery relatively quickly. So I guess the next thing to do is to actually hook it up to a speaker. Okay, the tinny little speaker is hooked up in place of the dummy load, and there is quite a significant amount of hiss coming out of it. Not that you guys can hear it because of the loudness of the power supply fan. And there's a faint hint of the 1 kilohertz signal, even with the control all the way down. We're already into distortion. All I need to do now is just remove this capacitor out of circuit, and there's a little bit more on the volume pot until it distorts. Alright, let's try a different type of speaker. Okay, so I've got one of the TX speakers hooked up. That is significantly loud for 1 kilohertz. So let me just change my generator frequency to something else. Right, not bad for a gain of 20. So it doesn't sound too bad into a, well, I want to say proper speaker, but yeah, a decent type of speaker, and it seems to drive it fine. So next I will probably play some sound through it. Oh, poor little thing. I just came out here for a quick smoke break and found this dead bird laying on the deck here. Oh, how sad. Rest in peace, little birdie. I'll bury you later. Maybe not, the neighbourhood cat might get you. Alright, doing something different. I got this crappy radio kit that I built the other day with the TDA 2822 removed. I'm coming directly off the output of the FMIC's output, the left channel in this case, going through my pot. Sounds perfectly clear and undistorted. However, that's not the full volume of this thing. That's 0. That'll be maximum. Significantly powerful. Now I don't know if I'm going to get hit for copyright for that. I might try and find another station which I know I'm probably not going to get hit for copyright. That was kind of a handy find. I can use the Vision FM Christian channel.
How do you communicate this to
your
talking fellow Australians or fellow people around the world who might be searching?
Now, so this stupid kit would have benefited better from an LM386 running at say 4.5 volts.
Read this book because... Why?
Yeah. Well, first of all, we've tried to write something that's
because this particular TDA 2822 chip is crap. I don't know why it doesn't operate correctly. I have messed around with it on a breadboard out of the circuit. No matter what configuration I put it in, it's just distorted, like it's not being biased correctly. So whatever.
It can be read devotionally and also in a Bible study type of context. Each of the chapters in the book, and there are 10.
So as we can hear, it sounds perfectly fine. The LM386 IC is a good power amplifier IC if it's treated correctly. As many preventative measures as possible are taken to stop it from oscillating. However, with its current gain setting and off that radio kit thing, it's driving to some pretty significantly high power. I mean, it's not loud, but it'll, into a smaller speaker, into a smaller enclosure, it would be loud enough. I reckon you could use it for anything. Anyway, I think that's where I'm going to leave this video here on the humble LM386 IC. So I hope you enjoyed this video, and thank you for following me with this journey through with it. Anyway, as usual, if you haven't done so already, please remember to go down below and rate, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying, see ya, have a great day guys. I'll see you in the next video. Thanks for watching.